Hello, I am Pavel Pomorsky, and the topic today is installing your software packages with Spack. First, let me give you an abstract of the talk. So what is Spack? Spack is a package management tool designed to support multiple versions and configurations of software in a wide variety of platforms and environments, and in particular, high-performance computing clusters, HPC clusters, which of the kind that the Alliance, Digital Research Alliance of Canada provides. Now, the clusters already do have a large software stack built over the past 7 or 8 years, and that uses Easy Build for package management. And I just want to make clear that there's no plan for us to currently change that. So for the next few years, Easy Build is going to be our default method to build packages. However, Spack exists as an alternative to Easy Build, and I believe we should pay attention to its capabilities and to what it does, explore the possibilities of how it could augment the existing Easy Build software stack. Plus, as we will see, Spack is a tool which can be used by users without root access, and there may already be users running Spack on our systems to install software. So for users like this, we might want to offer support and assistance. And I included the links to the Spack documentation and tutorial if you want to find out more. Now, a disclaimer here, I am not a Spack expert by any means, but I do have some experience with building packages for our current software stack using Easy Build. And I did spend the last few weeks learning more about Spack, trying to compile packages on the Linux machine and also our cluster using Spack, and encountering some success and some failures. So the purpose of this talk is to share my experiences basically of how it went and my thoughts on how Spack could potentially be used on our clusters and how users could benefit from it. So before I get into Spack specifically, let me just review the basic challenges of building scientific software. So scientific software is getting ever more complex. There's many dependencies when you build the software, many variants. It's hard to handle this if you're a user or staff at the supercomputing center. You want reproducibility, that's quite important. So if you are redoing your calculation on a different system, you might want to have a way to install exactly the same packages, at least as much as possible. In an HPC environment, all of this has to be highly optimized for the hardware it is running on, and it needs to be built efficiently and reproducibly with as little effort from staff and users as possible. So a cluster software stack is a particular challenge because you have to build a multitude, thousands of software packages in different versions, and as they are, used by various users. Clearly, there's so many of these packages that there has to be some automatic way to do this. You cannot do this by hand. It must be highly automatized for building a huge software stack, so that, for example, if you want to recompile everything for a different architecture, there should be an easy way to just do this for all packages. And the current tools that we use do allow for this, but Spack could potentially allow for this as well. And then there's the view on this from a single user. So if you log into a cluster, of course, you do have access to our software stack, which is quite large, and hopefully that software stack contains all the software that you need. But of course, that's never going to be entirely possible because users have individual needs, and our software stack, for example, we usually install, one version of a certain kind of software to serve everyone. But if you have special reason to use, let's say, that software compiled with a different flag or with a different toolbox attached, we might not be able to include this as a module. And even if we are, this installation may take time because our staff time is limited. When you request something to be installed, it might just take days, weeks until it is installed. So this slows down your research. So having a way to install things yourself is highly beneficial. And what if you are running not on a cluster, but on a Linux machine at home? You still might need to build software directly from source because the Linux distribution usually has only a single version attached to the distribution. Now, this version is usually well tested, highly reliable, easy to install. But if it is not what you need, then you will have to build it yourself. Or what if you need the latest version of some software for some reason, or you need a particular combination of versions to ensure reproducibility. So if you want your program to run exactly the same as it ran before, you probably would want to use the same dependencies. And on a Linux distribution, that might be difficult. Now, containers are an alternative, but of course, those also need to be built, that they don't come for free. And if you use a pre-made container, it might not be optimized for the hardware you're using. So that might be suboptimal. So even if you are a single user, having some kind of an automatic build system to build your packages and their dependencies efficiently could be very useful for you. So let's talk about Spack specifically then. So what is Spack and what features does it offer? So Spack is a package manager, and the key feature of it is it is built from the get-go for HPC environments. So it was designed for the complexity of building software on a cluster, which is exactly what we need. One very useful feature of it is that root access is not required to use it. So if you are a user, you can just log into our clusters and try to use Spack, and you should be able to do everything. There's nothing that will slow you down if you don't have root access. Spack installs every unique package into its own prefix, so multiple packages can easily coexist. Even packages compiled with different flags can exist at the same time, which is useful. It can install from source, which can be slow. So it also has the ability to use the binary caches, as we will see. So essentially, if it can be pointed to some repository which contains a previous build, it will not try to build that build from source, but it will just download the binaries from the cache. Now, one distinguishing feature of Spack is that it uses relatively simple installations, as we will see. The philosophy of Spack is you want to tell it briefly what is required, and it should figure out all the details. Now, as we will see, sometimes this works well, which is what you want, and sometimes there's some glitches and you have to do some tuning. But at least the idea is the goal is simplicity. Now, Spack is not an operating system, so it will run on top of existing OS, Linux, Mac OS, Windows. I will only talk about using it on Linux. And it doesn't do the actual building, so it relies on build tools like make or cmake or everything like this, which it just calls. It also relies on the host system for essential libraries, so you must have certain things installed in your Linux OS for it to work. And also, one major drawback of it, which actually would probably make it a no-no to be used as for our main software stack, is that it performs native builds, but not cross-compilations. So basically, it builds the software for the same processor that it is running on itself. Now, support for cross-compilation might be added in the future, but it is not there now. So this is in contrast to our easy build software stack, where essentially easy build can build software for many different architectures, and then we can make a repository of this, and this repository can be used on many different machines with different architectures. This currently Spack doesn't support. So how could Spack fit into what we are currently doing in the Alliance? So again, I want to reemphasize that easy build remains the main tool for building our software stack. We have been using it at least since 2017, if not before. A lot of staff time has been, invested into making it work. We have a lot of utility scripts associated with it, and we are unlikely to be moving from easy build anytime soon. But what we could do with Spack is maybe find some niche uses for it. So I'll give you an example. On Trillium, which is our large cluster, sometimes there are events where the cluster is reserved for running very large applications. And for this, you need to build a special software stack to run just those applications sometimes. And for this kind of special use, Spack, so building for a kind of a limited software stack, Spack might be a more convenient way to do it. And in fact, Signet has an experimental Spack configuration. This was an effort led by Mike Nolta. So if you want to check that out, here's a GitHub link. So that would be one way to do it. Another possible need is software for novel architectures. So on our DB clusters, we have a few nodes which have AMD APU chips. So these are chips which combine a GPU and an APU. And for those, software needs to be built using ROCm. Now, there's an issue here because EasyBuild, currently at least, as far as I know, does not support ROCm. There's work to include ROCm within the EasyBuild toolbox, but it's not there yet upstream. And if it's not upstream, if it's not available upstream, it's a bit difficult for us to implement it ourselves. I mean, we could, but it could take considerable effort. So Spack, however, does already offer support for ROCm. So if we wanted to build some software for those AMD APUs, we could conceivably use Spack for this. And finally, as I mentioned, Spack doesn't require root access. So there may already be users building Spack packages, using Spack to build packages on our systems. But as we will see, there are some improvements. You can always use to build your Spack packages better, have your Spack run more efficiently, and we could help assist users with that if there was a need. So, so if you are a user, how could Spack be potentially useful for you? So as I already mentioned, the default Alliance software stack is provided via EasyBuild. And if you need software, you can submit a ticket. You can say, I need this software, this version, and we will try to accommodate you as best we can. But as I mentioned, this is time consuming and we might not actually agree with installing something as a module. For example, if there's an existing module which would require some conflict with a new module that you want. So in theory, you can use your own EasyBuild packages. So if you know EasyBuild, you can define your own EasyBuild build file and run an EasyBuild command, and this will install a package as a module, and the package will be stored into a .local directory. But this is a bit of a cumbersome process. We don't advertise it widely. Unfortunately, EasyBuild is not particularly user-friendly. Sometimes if we want users to only install the software in their own space, we will provide an EasyBuild file for you and just say, run this command, it will install it in your .local directory. But for the users to work on EasyBuild directly, it would be a challenge. I mean, you're of course welcome to try, but I think it wouldn't be easy. So Spack could be an alternative here because it does not require root access. So you can run it on all Alliance clusters to install software. And it could be a possible alternative. So what are the possible use cases? So as we will see, Spack handles multiple versions of software really well. So let's say that for some reason you need to test 10 different variants of some piece of software. Let's say you want to try different versions, different compiler flags, different compilers. Spack could be very good for this. Also, what if you need a very specific version? So for example, let's say you need, I don't know, CMake, a utility like CMake. And you need the very, very, very latest version for some reason, and you find that this is not installed as a module by us. Trying to install it with Spack could definitely be worthwhile. And as we will see, it could be very easy. So it could be just with a few simple commands, you could be able to install this kind of utility or something else. And finally, there might be software out there where Spack is the preferred way to install it. So when you go to their documentation, they actually suggest that you use Spack to build it. So if that's the case, then knowing how to run Spack on our clusters could be useful. All right, so let's start looking at some concrete commands. And hopefully this slide will show you just how easy Spack is to use. So Spack doesn't require any complicated installation. You just do a git clone and you run a few commands and you can use Spack. So in this sense, it is quite nice. Again, no root access required. So the basic command is you run a git clone, you pick a branch release. Here I pick the latest 1.0, and I will talk in a moment what's the other option here. You specify the URL from which you're cloning, and you specify where you want the Spack directory to be. Here I use the home directory, but as we will see on a cluster, this might not actually be desirable. But if you're running on a Linux machine, just a desktop, you can put it in home. And that will be the directory into which all the packages are installed. So it might need to go quite large if you are installing a lot of packages. So after you do the git clone, you source the setup shell file, and this makes git Spack visible. One more command you need to run. You need to pin your package directory to a specific version. I'll say a bit more about that in a second. And you need to run one command, which is Spack compiler find. So Spack needs to have a compiler at the start. So this it will usually find the system compiler, which should be available on a Linux machine. If it isn't, you need to have one installed. And that's all the setup that you need to do. And at this point, you should be able to type Spack install, and then whatever package you want, Spack install CMake, for example, and then it should build the package from source and install it for you. It might take a while. Some source builds take a long time, and a lot of dependencies might be pulled in. So a given Spack package might have 100 dependencies, which Spack will build all from source. So it might take a while, but if it all goes well, that's all you need to build a package. So let me now expand on some points which I made here. So which version of Spack to use? So it is a little bit unfortunate that Spack has recently made a major milestone release, version 1.0, just in July 2025. So this made some major changes. One particular change, for example, was that package recipes files are now in a separate directory. So major changes means there have been some change in Spack configuration layout. So for example, that means that you have to make sure you're looking at the correct documentation because something has changed. And in particular, if you are using an AI assist, which I think a lot of us will be, sometimes AI will show you outdated information because it doesn't know whether you want release 0.23 or 1.0. But the major issue, though, is whenever, because this major release made changes, some package recipes have not caught up with the changes. So some builds might be failing with the newer version. I mean, at least one common piece of software which I tried to install, I just was getting weird errors with version 1.0, but when I was using version 0.23, it was working fine. So hopefully this is something which will be, resolved over the next few months, but it's just something that we have to live with. Let me also mention storage. So as I discussed, the Spack installs packages into directory where it was unpacked by Git. So that's nice because you can put this directory anywhere you want. It doesn't have to be in your home directory. And you want to put it in a directory which has a lot of space because Spack will consume gigabytes of memory, tens of gigabytes, especially if you are installing large packages. Then there's a .spack directory, which isn't going to be big, but this one does live in your home directory, and it just stores configuration files. And then Spack also generates a lot of temporary files as it's building the software. And by default, it puts it into /temp, but you can change that by defining the temp variable. And as we will see, you should do this especially on a cluster because the temp memory might be limited. And yeah, so Spack will use a lot of disk space, so just make sure that you are ready to handle this. And then compilers. So as I mentioned, the initial compiler has to come from outside of Spack. This is a bootstrapping issue, I guess. So to build something, you need a compiler, and Spack cannot build a compiler without having a compiler. So at least the first compiler has to come from the operating system. And in that way, that such a compiler is considered an external package. So Spack can use external packages, as I will discuss in a second, and so the compiler is one of those. Now, Spack will actually look for all available compilers on the system. So, if you are using a Ubuntu Linux box, there will usually be only one initially. But if you are running this on our clusters, there might be a whole bunch. So it will try to find all of them. And you might need to tweak the configuration to make sure that everything is pointing at the right executables. And I will discuss this in a moment. But then once you have the first compiler working, you can install your own compilers within Spack if that's what you need to do. So I mentioned external packages. So not everything used within Spack has to come from Spack itself. Spack can use external packages. In fact, you can declare any package which external and which as external. And this is highly useful in an HPC cluster because, for example, let's take MPI. Now we have highly tuned installations on MPI on our clusters, and this is the ones that we want you to use. We don't really want you to compile your own MPI. You can, but this MPI is unlikely to be optimized for our systems. So within Spack, you can declare MPI as an external package and then use the one that we have installed as a module. And not only will this save you time because you don't have to build MPI, it will be using the one we have built, but then you'll be using what should be the most efficient MPI on the system. And this can be extended. There's many other packages we already have installed. I mean, for example, let's say CMake. I mean, you need to build your own CMake, a tool like this. It might be sufficient just to use the one we have. So you can define a whole list of packages as external, which means that Spack will just use whatever is available on the system. Now, there's a drawback here. This somewhat reduces reproducibility. So if that's a concern, you might want to avoid external packages. So, if you want to take your software from one cluster, from one supercomputing center to another and get the same results, well, if you are using an external MPI compile, then it might not be the same from one cluster to the next. So you might want to build your own. So there's a trade-off, you have to decide what you want. So Spack packages, there's about 8,000 of them. So there's a large variety of scientific software that is now supported by Spack. So this is the link if you want to explore that. As I mentioned, since version 1.0, the build recipe files have a separate directory. So there's the GitHub link. And as I mentioned, when you are installing packages, you might want to pin your Spack installation to a specific release of packages for stability so that the packages are not changing, from on you as you're installing. And of course, you can write your own recipes to build your own software as well. So, this could be good, for example, if you are in a research group, which let's say you want to make the building of your own software package easier and more reproducible, you can write your own recipe. And for example, if you want to, have more research groups around the world use your package, if you provide a Spack recipe on how to build it, well, it will be easier to build. So maybe more people will be willing to try it. So here's an example package. This is NAMD. You get the basic information about it. So you can see which versions are supported by Spack. That's listed here, who is the maintainer. It shows you the major dependencies, and it also shows you the variants. So one of the key things about scientific software is that sometimes you can build it in many variants. So for example, NAMD can be built to run on a CPU, or it can be built to run on a GPU. So you need different builds for each case. And then there's different GPUs. So there's AMD GPUs and there's NVIDIA GPUs. So you need a different build for each one of those cases as well. And there's also some other things you can tweak. For example, the type of GPU you are targeting. So are you targeting an H100 and an A100? So you can specify the architecture. So essentially looking at the space page, you can find out which variants of the software exist and how you can tell Spack which one to build. So let me give you some examples of package building. So essentially we have a wide variety of options, and they grow from the simple to more complicated. So for example, if I just want NAMD and I don't care about which version, or I'm just willing to take the version that Spack decides is the default, and I'm just willing to take all of the default choices for compiler configuration that Spack has, then I just type Spack install NAMD, and that should hopefully build that for me. But let's say if I want version 3.0.1 specifically. So of course, this has to be a supported version. So as we see on this page, I can see which versions are supported. I can see that 3.0.1 is. So I can request build version 3.0.1 for me using this @ symbol. and it will do this. And then let's say I want to build NAMD with CUDA support targeting CUDA architecture 9.0, so H100 generation. I do this. So I say I want 3.1 and I do a plus CUDA. So make a CUDA install and then this CUDA architecture. It will build that. And then let's say I want to build an AMD version with ROCm. So I say install ROCm, use ROCm, target this generation of AMD APUs, the MI300 generation, and it will do that. Notice that these installs will actually install the entire ROCm stack. So when I was actually trying this, this installed something like 120 packages, including the entire ROCm toolbox from source. Now, that is something which is very difficult to install from source if you're trying to use it manually. So the fact that Spack can just do this is pretty amazing. And this is actually why we are looking at it to at least build the initial software stack for the MI300A's GPUs. And of course, a compilation like this, where you need to compile so many packages, will take, a few hours, but that's something to get used to. But also keep in mind that it needs 120 packages, but once a package like this is built, it can be reused by future installations. So for example, if I run this will build some packages which can be reused by this installation. So you only need to build a package once for a specific configuration. So to make it more formal, these symbols that you were seeing are called sigils. So whenever you run a Spack command, if you want to enable something, that's a plus. If you want to disable something, so if something is on by default and you want to disable, you use a minus or a tilde. Versions is at. You can also specify dependencies. So let's say I want to build NAMD and I specifically want to use the GCC version 14.3.0 as a compiler. I can do this, %GCC, and this will tell it to use a compiler. You can also have transitive dependencies, which are dependencies of dependencies. So let's say if you want to use a specific version of MPI for everything, you could do that. And you can also even specify specific flags. So let's say I want to use NAMD. I want to build NAMD with a higher level of optimization. So I want optimization level 3. I just add C flags and Spack will build it with a higher level of optimization. So let's actually look at this specific case. So let's say that I build NAMD version 3.01 first, and then I build again NAMD version 3.01 with optimization flags -03. And then I look at what Spack has actually installed, and Spack shows me that there's now 2 NAMD packages installed. So there's this one, the default one, and then there's this one, which was built with a different optimization flag. So how does Spack keep track of these two? Well, Spack assigns a hash to each package it builds. And if you use Spack find, you can do the -L option to show you what this hash is. And so here are the hashes. So here's the unique ID for this installation, and here's the unique ID for this installation. So these hashes are not very informative. So let's say I actually want to know how do these two installations differ. Well, Spack has a very useful diff command. So I can do Spack diff, and I will just ask, what is the difference between this version and this version? So the slash you put in front of the hash to have Spack recognize it as an ID of an installation. And it shows me that, here's a difference. This one was built without the -03 flag, and this one has been built with the -03 flag. And also these hashes can be used when compiling software. So for example, going back to this, if here I'm specifying a dependency with a percentage sigil and actually saying, and I want GCC version 4.30, GCC also has its own hash. So if I wanted to, I could just directly put a hash of this particular installation in this build, and it would use that particular one as a dependency. So this could be a very useful tool, especially if you are doing some experimentation. So for example, let's say if you're curious, you have some software and you want to try different compilation flags and see, does this change the performance? So you could, of course, do this by hand. You could create one directory into which you install the software with this set of flags and another directory where you install with this set of flags, but then you have to keep track of what all these directories are, and it can be quite annoying. So if you are doing this type of work, then having this kind of a system which can really track your different versions and do diffs between them so you know exactly how they differ, that could be very useful. Okay, so far I'm making this sound simple, but unfortunately it might not be. There might be some difficulties with Spack. So Spack may not just work. So we can compare this the situation here to Linux distribution. Now, when you are using Ubuntu and you tell Ubuntu, install a package that is part of the distribution, you're basically certain that this will work because this has all been tested. There's only a single version. The operating system is known, and there's no reason why this wouldn't work. Unfortunately, with Spack, you have a much larger configuration space. There's many more permutations of options. There's many different versions. There's many different versions of dependencies. All of this is running on many different operating systems, which some of them can have some strange setups. So there's simply no way, at least currently, for Spack to test for all of these configurations. So there will be some combinations of options or some operating system setups for which your Spack installation command will not work. So essentially, some fiddling with Spack is usually required to have it working, except for simple packages. You might have to, for example, try different versions of packages. You might want to use an older version of CUDA. So essentially, the recipes, for example, that people write to install this software, I mean, there's a limit to how intelligent they can be, and there will be some combinations of dependencies which they just cannot handle. They are not smart enough to handle them. And of course, this will vary from package to package. There's 8,000 packages maintained by thousands of people. And like some of those people, I guess, have more time to maintain the package than others. So some packages might be more reliable than other packages. So the mileage here can vary. And of course, you have a chance to contribute yourself. So if you find that you are having trouble installing some software and then you figure out why that is, well, you might want to make a pull request on GitHub to actually suggest improvements to that package recipe. Let me also mention Spack environments. So far, when I talked about installing packages, so when I would run Spack install namd, it will install namd, assuming it works successfully, but I don't have namd available on the command line, at least not by default. I have to do some setup to make this happen. And the tool to handle this is called Spack environment. So this is somewhat analogous to Python environments. Essentially, it's a way to create a selection of packages to be used for a particular task. And these executables in this package will be included in your path. So once you get your environment working, once you set it up, if you type namd within this environment, that executable should be found. Now, there's limits to this because an environment, a Spack environment can install multiple versions of packages. So for example, if I installed multiple versions of namd like I did in the previous slides, if I just type namd, there will be ambiguity, which one should be launched. So in such cases, there's additional work you actually need to do to define what are called Spack views, which I won't go into. But here, let's consider a simple case where everything can just go into the same path. So to create a project, I run Spack and create my project. Of course, I could call it something else. I can then list the environments, just check that's there. Then I activate the environment, Spack, and activate my project. And then I specify what I want to have in the environment. So I don't run install yet. I run Spack add. So here it's basically adding to the specification of the environment. I want, let's say, TCL to be in this environment, and I want the Trilinus package. And then I can run Spack install, and this is the step which will actually install these packages. But typically, though, I want to do something before I do Spack install. So when I do Spack add, this actually generates a spack.yaml configuration file, which is basically a recipe to build that environment. And you probably want to take a look at that file and make sure that everything checked out and it's building the way you want. There's some options there how you handle dependencies and how they interact with each other. And when you build the environment, there will also be a spack.log file, which will contain the provenance information. So information about how the environment was built and all its details. This can be useful if you want to move the environment to another system and rebuild it there. And in fact, it's also possible to take your Spack environment files and export them into what is called a mirror, so that if somebody else wants to recreate that environment on another system, they don't need to rebuild everything from source. They can just point at the mirror and grab the binary files from there. So this can be highly useful as well. All right, so now let me talk about the specific case of using Spack on Alliance clusters. So what are the differences? So here I run the same command as I did before, but I specifically put the Spack installation directory on project. So project is the natural place to put it, not home, because on home you have a relatively small file limit, disk limit, but on project you will have at least 1 terabyte. So project is a good candidate to put your Spack on. So here I initialize Spack as before. And then here I want to define a temporary directory to store temporary build files. So by default, this is /temp, but on on cluster login nodes, that is limited, and you might just hit that limit. So it's better to use Scratch, where you will have a much larger limit. Again, I pin my repo to a specific version. I do Spack compiler find, of which more in a second, and then I install the package you want. So it looks very similar to what we did, what we would do, let's say, on a simpler Linux machine, except for specifying the installation and temporary directories. So what happens with compilers on a cluster? So here's a screenshot of what you would see on Nibi. So after I install Spack there, I run Spack compiler find, and actually, in this screenshot I would have run this. I have run this command before, so it actually doesn't find anything new. But it tells me that these compilers will be defined in .spack packages.yam. And then I do Spack compiler list, and it shows me all the different compilers that have been found. And on our systems, in our default software stack, we do have different versions of GCC available. So one of these is the system GCC, so the one which came with the original OS, and then the others live in CFFMS. So for example, I can get some information about the specific compiler. So I can look at GCC 1430, and this tells me that this is indeed the one which is defined in CVFMS. Now, I might want to tweak this file, because notice that this is using, because we have many different versions of GCC on our systems. To separate them out, the executable is not named GCC, but it's named GCC-14 in this case. Now, this might work with some cases, but some Spack packages expect the compiler to just be called GCC. And so you might want to edit the the packages.yam file, and you might want to point it to the actual GCC compiler for that particular version, which is just located in a different location. So you just need to change the location. And you can also actually add a module load command as well. So you can edit this file to add a module load command for a particular package. So Spack is not smart enough by itself to find out that there's modules on the system. It just looks for executables. So you might want to give it a hint that there's a module. So another difficulty arises on clusters. So as I mentioned, Spack is hungry for storage. So you need to give it a lot of storage. And in fact, watch out, you might sometimes get strange errors when you run out of storage. And I mean, sometimes it will tell you no more disk space or whatever, but sometimes it just fails for some strange reasons. And the underlying reason might be that you've run out of storage. So you need to make sure that you have enough space for root and temp. So as I mentioned, I'm just reiterating what I said before. For the Spack install directory, use project, never home, and always define the temp directory to point to Scratch. You can also clean up after yourself. So if you want to clean the temporary files after you finish building, you can run this command, spack clean dash.stage. So this will clean out whatever is in the temp directory. So it's very useful to do this once in a while on any system, of course. And you can also do garbage collection. So if you have some packages installed which are only necessary for building, but they are not necessarily for running the software, then once you have finished building, you can run Spack GC for garbage collection. This will remove those packages which you don't need anymore. Don't run it too quickly, because if you need to build something again, you don't want to reinstall all those packages. But if you're sure that your building is done and you will just be using the software, you can run this garbage collection. All right, so last slide, let's talk about Spack caching. So what are the possible issues with using Spack on clusters? So Spack builds, they can take a long time and they consume a lot of disk space. So if the usage of Spack gains traction and we have many users running Spack, then they will be storing multiple copies of the same packages, and this will be using up disk space and it'll be wasteful. And of course, the building takes a long time. So if people are building a lot, this will of course just take up their time and also take up computational resources. So Spack has a very interesting mechanism to get binary files from somewhere else if they have already been compiled. In particular, I mentioned already mirrors, so you can take a Spack environment, you can export the build files to the mirror, and then if somebody wants to recreate that environment, they don't need to build it from source, they can just grab the binaries. As an extension of this, a Spack installation can actually be sort of joined with another installation. It can be pointed to another installation. So if you have some other installation which has already built the packages you need, then you can tell your installation before you build it, look there to see maybe the package you need is already there. And if it is, then Spack will just use that one instead of building your own, which will save you a lot of time and disk space. Now, just as a caveat, this file duplication is a bit of a less of an issue on system with which have vast storage, because they have what is called the deduplication mechanism. So if multiple users are storing the same file or similar files, it will actually be stored only once, and then the other users will have a link, kind of a link to that file. So we are worried a bit less about this kind of duplications on system like Nibby and Trillium. So the application here I can think of, for example, is if you have a research group and multiple people are building the same package or need the same dependencies, you could set up one Spack installation, which everybody in the group has access to, and then you could put as many packages as possible into this shared installation, and then each user building their own packages, they would save some time because they could grab some of the dependencies from that shared Spack install. And then on the alliance level, if we saw that there's a sufficient need for this, we could maintain this kind of central repository ourselves, holding some commonly used packages, so that if you are using Spack on our systems, you could just in your configuration file point at the central Spack installation. And so when you're running your Spack install, if there's something that you need, but we already have it in the central installation, it will just be grabbed from there. You won't have to install it yourself. So this could save users a lot of time, hopefully. So, so this is almost the end of my talks. I want to emphasize here that hopefully you can gather from this that software installation is a complex problem, and we are open to user feedback. Let us know what works, what doesn't work. Let us know if Spack is something that you are interested or that you're already using, and what kind of support you would need for it or other build options. As I mentioned, we can maybe work on setting up this central repository for Spack packages. And we could also maybe assist you with Spack configurations, because as I mentioned, there can be quite a lot of tweaking done to really optimize your Spack installation on our systems if you're using Spack. Okay, so I will stop here, and I am open to questions.